Okay guys, welcome to, this would be module 4 actually, so this will be our 4th week into this class. Hopefully you're enjoying it so far. Hopefully you're learning a little bit about the world around you and maybe a little bit how the world actually applies to you in a way. And later on this semester, I'll promise you, it will get so that we are more relating things more to us a bit more. We need to understand some of the basic processes first and the basic concepts first, but we will try to get it, apply it more to you and in your settings. So also something that I need to remind you is next week is our first exam. That's next Tuesday, and we'll discuss more about that. I'll do a little bit of a quick video overview of how the exams are set up a little bit later. But I just wanted to remind you of that and start preparing now. The objectives inside of our modules is what I use as a study guide. If you understand those questions and you can answer those questions, then you should be doing pretty good on the exam. Okay, so today we're going to be talking about what basically I think it's chapter 4 in the text, if I remember right, which is basically talking about igneous rocks and the igneous processes that occur within there. So last time we talked about portions of the rock cycle, the sedimentary portion of the rock cycle. Okay, let me get my laser pointer here. So this portion is what we talked about last time, the weathering, transportation, deposition to create sediments and sedimentary rocks. And we learned that if we actually look at those sedimentary rocks, we can learn a lot about their past and their history. It's the same case with igneous rocks. Now igneous rocks, remember, sedimentary rocks were a rock that was changed in its physical form, or in its actually solid form. So it actually was weathered, still in its solid form, usually in some case either as an ion or as a particle or a clast, and cemented back together. So it was always in its solid form in a sense. Okay. Now an igneous rock is a little bit different. It is a rock that has been heated so much that it's now in its molten form. Okay, those minerals that were inside the rock are now in molten form. It's too high of temperatures, and as they actually go up in the subsurface, up here in the underground, they will then cool off. And as they cool off, they will become what we call intrusive rocks or extrusive rocks. I also call these different things. The different textbooks have them different ways. I call them either plutonic rocks or volcanic rocks. Now, if anybody who's ever done anything with Greek mythology or Roman mythology, you know that there's different gods for different parts of the world, right? And if I remember right, the Roman gods for the underworld, his name is Pluto. And Pluto is where that name plutons or plutonic rocks come from, because these rocks will cool underground. And if they cool underground, they actually have it's time to cool off for a longer period of time. The crystals get larger, and we'll talk more about that. But they cool off underground, so we call these plutonic rocks, based off of Pluto, right? Now, if they get to the surface, we call that molten material underground is called magma. But if it gets to the surface, we then call it lava. And that lava, when it cools off, is called a volcanic rock. And so now remember that your Roman god of fire is Vulcan, and so that's why we call them volcanic rocks. If they cool on the surface of our planet, we call them volcanic rocks. They've intruded in some way from a volcano. Okay, and then that intruded word that I use is to extrude out or to come out of, is where we get the term extrusive rocks, and intrusive, which is inside, right, is where we get the term intrusive rocks. We use those terms interchangeably a lot of times, and I'm doing quite a bit, so I wanted to make sure that you guys understand the roots of those words and where they come from. So we're going to be talking about this portion, the igneous rocks and the processes involved with those igneous rocks. So, I love flowcharts. You've already probably seen a flowchart in the last one when we talked about minerals and also when we talked about sedimentary rocks. And so, any existing rock, okay, can have melting occur to it. Or you can have melting that could then become a rock, right? Okay, either way. So that melt here is going to happen because of 3 different ways. There's 3 reasons you have a melt, okay? You can either have an increased temperature, so increase the heat, the rock or the material inside that rock is going to melt. So for example, this rock right here is an igneous rock, and if I actually heat this rock up to about 1200 degrees Fahrenheit, or Celsius, you can then melt this rock in its molten form, right? And but as it cools off, certain materials will come out, and because different minerals inside of this rock have different melting points. And we'll talk about that a little bit later. But one of the reasons a rock can melt is because the obvious reason that you have increased heat. Okay. Now remember that increased heat from in our subsurface usually is from radioactive decay. That's the #1 cause of our heat in our subsurface, is the decay of those elements. Okay. Now another way that you can have melting is decreased pressure. So when something is hot, if you decrease the pressure, the melting point changes. And so if something's under a lot of pressure, it can't actually melt. But if you start decreasing the pressure, the melting point will actually go up. And so something can actually start to melt because of that decreased pressure. So it's not an increase in pressure, it's a decrease in pressure that causes something to melt. And we'll talk about some circumstances where that happens a little bit later. The last one is by adding water, and we can call them volatiles. Anything that actually will lower the melting point. Water just happens to be probably the most abundant and the most common volatile. Okay, by adding water to a melt, the melting point will go down. The melting point will go down, causing more things to melt. Okay, and so that's something to think about. Those are 3 things you should know. By the way, those are important 3 concepts. These flowcharts are important because they help us to understand where we are and how much, and also where certain rocks are going to form and things like that. So these are important concepts that will promise you'll be on the exam. Okay, so that melting is caused by increased temperature, decreased pressure, and added water. And it's always underground. You always have that melt occurring underground, right? Now, if it does melt, it then becomes magma. Okay, because magma is on the subsurface, and if you remember Austin Powers, you have the vat of magma, right? Anyways, it's that Dr. Evil is trying to kill Austin. Well, that doesn't actually work because that magma that he says is at the surface, and therefore, what in reality is magma. It should actually be called lava, because if it rises to the Earth's surface, we then call it lava. Now, if something is moving up in the subsurface, it's usually because it has a lower density. And you can have lower density for many different things. It could be your actual chemical makeup of the material that could have a lower density, or it could have a change in temperature, and temperature also causes densities to be lower. And so either one of those can cause magma to rise in the subsurface. If it reaches the surface, it becomes lava. Okay? And if that lava erupts from the underground, we call that a volcano. And therefore, those rocks cool off to become what we call an extrusive or volcanic rock. Okay? And we'll show you how to identify those in a bit. But if that magma cools off underground, okay, below the surface, it will become what we call an igneous or plutonic rock. So remember, Pluto is the god of the underworld, okay, cools off underground. Vulcan is the god of fire, and cools off on the surface. Okay, so intrusive inside, extrusive outside. Okay, those are things just to help you remember some of these concepts and these ideas, and we'll go back through these later. This is just a summary of volcanics volcanic rocks in a quick summary. So, as we talked about before, when a magma actually cools, it will actually cools off. It will become an igneous rock, right? Okay, and igneous actually means born of fire. Okay, so it's molten in some way. And so above the surface, we call that volcanic rock after the Vulcan, right? In Greek, I think it says Hephaestus, if I remember right. Okay, and then if it's above the surface, it's Pluto in the Roman one, and it's Hades, if I remember right, in the Greek gods, right? And so if you notice, they look slightly different from one another. So I have 2 rocks here, and I'm going to show you 2 ones. One's an extrusive rock, which is this one right here. You can see it somewhat in the video. It kind of doesn't have very big grain sizes. The grain sizes are really small because when it got to the surface, it cooled off fast. And so the actual mineral grains couldn't actually cool off a lot faster, so you can't see them very well with the naked eye. However, rocks like this one, which is one that you can see a lot around this area, it's a little heavy. Okay, you can even see the crystals, and some of them are fairly big. And these are what we call intrusive rocks or plutonic rocks, and they cooled off underground, right? And they cooled off slow enough that the individual minerals can actually form inside of the rock, right? So each of these individual minerals will actually form slowly over time as they cool off. Okay, so those are the difference between what we call a volcanic rock and a plutonic rock. So that's important. That's one of the things that we can show you about the different types of rocks is their texture, but also based off of their composition. So notice that these rocks tend to be are dark, but you can have light-colored extrusive rocks, but you also can have dark-colored plutonic rocks. And so to realize the color doesn't have anything to do with if they're cooled underground or above ground, but the color has to do with the composition. So when we talk about minerals, color was not a very good diagnostic classifier, right? In igneous rocks, it's more characteristic, and we'll talk to you why about that in just a minute. Okay, so when you look at a rock, or the magma that actually comes with that rock, I'm going to move this out of the way for a second. Okay, the chemical composition of a rock is basically made up of two types of material. We call it either felsic or mafic. Then we can have extremes in that, which if it's really mafic, we call it ultramafic, and if it's in between mafic and felsic, we call it intermediate. Okay, so the things that's kind of important of this, the two end members, what we usually talk about, or what's more common in our crust, is either felsic material or mafic material. Felsic being silica and feldspar rich. This is why it's called felsic, feldspar and silica. Remember, silica is one of the most common materials in our crust. Okay, so it's very common in the subsurface. And if you look at the mafic end, you have magnesium and iron, right? So the mafic. And so the iron here itself, remember the subsurface, the further down in the subsurface you go, near our core and areas like that, have lots of iron. So our mantle also is very, very mafic, or what we do even call ultramafic. Okay, so because there's a lot of iron and not as much of silica. So this graph down here kind of helps us understand that, and you'll look at these different minerals that are common in these areas. Okay, now I'm not asking you to remember all these different minerals. I'm more asking you to understand the stuff below it. Okay, so felsic rocks tend to have high silica in it. Okay, they also have high sodium, but not very much iron. Okay, and they also cool off at a lower temperature, at about 700 degrees Celsius. That's an important concept for later. They have a higher viscosity, and we'll talk about what viscosity is in a second, but it's really the resistance to flow. But they have a lower density. Now think about that one. Why would they have a lower density? If you come up here and look at feldspars and silica, silica is lower, on the periodic table than felsic is. Felsic has, the mafic minerals do. Magnesium and iron are heavier items. They have more mass, or lower, or they have higher protons, higher neutrons than silica does. Okay, so these are more dense materials. These are less dense materials. So it makes sense that the felsic materials are going to be less dense, and the mafic materials are going to be more dense, right? And so the mafic materials have less silica in it, only about 50%. Now remember, silica is still tons of it, so it's only 50% here, whereas it's almost 70 to 60% up here in the felsic. Also, the iron content is much greater in the mafic material, and the temperatures in which they actually melt is a lot higher. Okay, viscosity is lower, which means it can flow a lot better. It's less resistant to flow, so it can flow, whereas the felsic materials can't flow very well. And it has a higher density. These are important. We're going to talk a lot about felsic rocks and mafic rocks, and even mafic and felsic volcanoes. And so these are very, very important concepts for this section. And some students have a problem with this section because they have a hard time with remembering these. But this is key. If you can remember, felsic is lots of silica, mafic is lots of iron, and therefore they have these trends of having a high viscosity for felsic, low for iron, low densities for felsic, high for mafic, and so forth. If you can remember these trends, you'll do very well in this section. Okay, so the last part that we need to understand is that properties of the magma, what viscosity is. And remember, viscosity is not how well it flows, it's how resistant to flow it is. So the stickier it is, the more viscous it is. So think about like honey or something like that. The thicker it is, the harder it is to move. The hotter it is, though, the more it moves, or the less resistant to flow it is. I'm going to stop here. We're going to start here again next time, but we'll see you guys in a bit.